Hey guys, so 9.2 is going to talk about sample proportions. Remember, a proportion is like a percentage. So if I take 100 people and I ask them a question, then I'm usually going to get a proportion of people that say yes or a proportion of people that say no. So in this section, we're going to focus in on situations where the statistic of interest is a proportion. For example, what percentage of adults population in Orlando watches The Bachelor? So we define the sample proportion as follows. P hat is equal to X, where X is the number of successes in the sample over N, and N is the size of the sample. So let's say in Orlando, I asked 100 people. So N is equal to 100. And let's say I asked them this question, how many of you watch The Bachelor? And let's say 13 of them say they do. 13 out of 100. So my P hat is going to be equal to 13 out of 100 or 13% or 0.13. The variable x satisfies all the conditions of a binomial distribution given independence. So remember that the four conditions for a binomial distribution are that we have a probability being the same. There's independence. Observations are fixed. We have a fixed number of observations. And our last one is, and we have success or failure. So remember the formulas for mean and standard deviation of a variable with a binomial distribution? Well, we can derive them and we come up with these rules for combining these distributions. For if I'm looking for the mean of p hat, it's actually just p. And the standard deviation of p hat is the square root of p times 1 minus p over n. These are in the formula sheet. They're right under binomial distributions. So if you look under the binomial distribution, it's going to say the mean of p hat is equal to p, and the standard deviation of p hat is equal to the square root of p over here, this formula. So to summarize, we choose an ASRS of size n from a large population with a population proportion of p. Let p hat be the proportion of the sample. Remember that p hat deals with the statistic and p deals with the population, or is our parameter. So then the mean of p hat, which is what I just said on the last slide, is just whatever p is. And the standard deviation of the sampling distribution of p hat is this. Here are a few guidelines for using these numbers. Use the formula for a standard deviation of p hat only when the population is at least 10 times larger than the sample. So 10 times n has to be less than or equal to big N. Remember, big N represents our population. The distribution of p hat is never exactly normal. Why? Well, think about a sample size of size 2. What are the outcomes for the proportion? Well, we could have 0 out of 2, or we could have 1 out of 2, or we could have 2 out of 2. So we could have 0%, 50%, or 100% be our proportion. Remember, something that is normal is going to have infinite amount of possibilities, and where we have with proportions, we have exact numbers. We have finite possibilities that either 0, 1, or 2 people are going to be answering whatever question we have for this proportion. So however, we can use the normal approximation when our two conditions from the binomial distribution are satisfied. Remember, n times p has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. In this case, our sampling distribution of p hat is approximately normal, with a mean of p and a standard deviation of the square root of p times 1 minus p over n. So using the normal approximation, a polling organization asks an SRS of 1,500 first-year college students whether they applied to any other universities. In fact, 35% of all first-year students applied to colleges besides the one they are attending. So 35% here, it represents our population, so we're going to say that P is 0.35. What is the probability that the random sample of 1,500 students will give a result that is within 2 percentage points of the true value? Before we even start this problem, we have to check both rules of thumb first. The first rule of thumb is that 10 times our sample has to be less than or equal to our population. So 10 times 1,500 is 15,000, and I think we can say that there's more than 15,000 first-year college students. And then our second rule of thumb is n times p has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. So n times p, 15,000 times our proportion, 0.35, is 525, which is much larger than 10. And then we have 15,000 times 0.65. 1 minus p is 0.65, which is 975, which is much larger than 10. All right, since we checked both of our rules and they both work, check. Now we can use the normal approximation. So remember, to find z-score, we're going to do x minus mean over standard deviation. And our x here is within 2 percentage points of the true value. So if we're thinking between 2 percentage points of 35%, we have plus or minus 2, 35 plus or minus 2, which is 33 to 37. That's where our x value is between those two. So let's first do it for 33. 33 minus 35, 0.33 minus 0.35 over our standard deviation, which is, let's calculate it real quick. Do that down here. The square root of p hat is equal to p, so 0.35 times 1 minus p, 0.65, all over n, which is 1,500. And that is 0.001517, and the square root of that is 0.0123. So I have 0.33 minus 0.35 over 0.0123, and that gives me a z-score of negative 1.62. And if I look that up in my z-score table, I don't have one, so I'm going to approximate here. And really quickly, let me draw my curve. So 1.62 is about right here, and the area under this is 0.0526. And now when I do 0.37 minus 0.35 over still the standard deviation is the same, I get 1.62, which is somewhere over here. And I want the area in between, so I'm going to go for this blue area. When I look that up in the chart, I get 0.947, like let's say 4. And I'm going to subtract these two areas because I don't want this part and I get an area of 0.8948. So around 89.48% fall between the 2 percentage points of 35%. So if we took a random sample of 1,500 first-year college students, 89% of the time we should find our proportion to be between within 2 percentage points, so between 33 and 37%, a proportion that say they only applied to that college. Using the normal approximation. So we can use these methods to check for undercoverage. Let's suppose 51% of all Americans are female. Suppose a proportion of p-hat of females in a random sample of 2,000 should be about 51%, or 0.51. And let's say we take an SRS of 2,000 Americans that includes only 800 women. What is the probability that such a sample has 800 or fewer women? Now, if we think 51% is about 50%, and 1,000 Americans, we should have at least 1,000 Americans be female if we were to take this sample. So let's test this. There's 800 or fewer. 800 is going to give us 800 out of 2,000, a proportion of 0.4. And our p-value is 51%, so that's our mean. Remember, the mean of p-hat is equal to whatever p is. And since they said all Americans, we know that the parameter is p. So we have 0.4 minus, we're going to do z-score, minus 0.51 over our standard deviation, which is 0.51 times 0.49 over 2,000. So I have negative 0.11 over 0.011. And I get a z-score of something crazy, negative 9.8. That is so far. If you look at our normal curve, and if you look at your chart, I think the lowest it goes is negative 3.5. Well, negative 9 is so far away, so that's definitely has undercoverage there, because that should not happen. If we have a sample of that should represent all of our Americans, then 51% of them should be women. So more than half, more than 1,000 should be in our sample. So it's rarely, almost never going to occur that we get only 800 or fewer women. So this is a good way to check for undercoverage if we wanted to test to see if our sample was accurate or not. So here's the homework for number 2, our second section, 9.2. There's only 5 problems, so try it out.